In this one, this video, we want to take what we know about quantum numbers and look at what atomic orbitals actually look like. Okay, so yeah, there's a lot of detail in here. Really, I want to focus on what are the generic shapes of what orbitals look like and how this relates back to what the quantum numbers told us when we talked about quantum numbers. All right, so we're gonna start off with s orbitals. I like to think that S stands for sphere, just a way to remember it. That's not what S stands for, but as a way to remember it, it works well. This means L equals 0 because there's one value of one value of M sub L possible, right? 0. There's one orbital per subshell, right? Remember that's 2L plus 1. These are spherical. What we're looking at here are some cutaway slices. These are different S orbitals, so this will be 1s, 2s, and 3s. Okay. And as you see, as we saw before, as n gets bigger, the orbitals get bigger, but the general shape of the orbital is about the same. Okay. You'll notice in the 2 and the 3, we have nodes. There's a node here, there's a node there, there's a node there, and we will talk about nodes in a minute. Okay. But really, S stands for sphere. Every S subshell has one orbital in it, and it looks like a sphere. Okay. P orbitals means that L equals 1. These are dumbbell shaped. They have 2 lobes that are opposite of each other. There are 3 orbitals per subshell, because remember M sub L is going to be -1, 0, or +1. So there's 3 possible values. There's 3 orbitals, or 2L plus 1 equals 3. And that's just because there's one along the x-axis, one along the y-axis, and one along the z-axis here. Okay. They all have the same general shape. They look like that. Okay. We don't have to worry about px, py, pz, because just know there's 3 of them. Okay. They all have the same energy. They all have the same general shape because they have the shape depends on what the value of L is. Okay. Lost my thing. All right. Let's talk about nodes for a second. It was really obvious. If we look back, the p orbital, every p orbital has 2 main sides to it. Okay. You can see them here too. There's 2 main sides to this, and they're split by what's called a node. So here's another look at the p orbital. There's your node in the middle. Okay. The node means there is 0 probability of finding an electron. Okay. And so what that means is in the p orbital, we can get electrons up here, we can get electrons down here, but we can't get electrons in the middle. Okay. S orbital is spherical. There's 0 nodes in this. And so we have it there. The node is officially where your wave function crosses 0. So here, if this is our wave function, every node is where this crosses 0. There's no wave characteristic there because the value is always 0. Okay. And something that people probably don't tell you is that the quantum numbers really are defining the nodes, okay? Or at least that's what L is telling us. L is telling us, not necessarily, we treat it as it's telling us what the shape of the orbital is, but the shape of the orbital is determined on the nodes, okay? So, or planar nodes, okay? I'm gonna get in the weeds, I'm sorry. Right, so if you think about it, every orbital could be a sphere, but a p orbital has 1 node in it in the middle, and so it gets pinched into 2 chunks, okay, because of that node in the middle, okay. I'm going to try not to harp on it, but just remember that's where no electron density could be. Oops. Next, we can talk about d orbitals. In a d orbital, we have L equals 2, so we can treat this means we have 2 planar nodes in there. Because L equals 2, we have 5 orbitals per subshell. They all are cloverleaf shaped. Okay, the one that's not is dz squared. Okay, dz squared looks like a p orbital, but it has a donut going around the center. Now remember we said there's 2 planar nodes in each one of these. For the 4 cloverleaf looking ones, they're easy to spot the nodes because they're where the lobes are split. So there's one here and here. There's nodes here and here, right? And there's nodes here and here. Okay, it's not too terrible. What we can't really tell about 3D z squared, excuse me, it's not intuitively obvious where the nodes are, but the nodes are actually a cone because it's a plane of nodes that is spun around, which is why we have the donut. So in the top of the cone is the top lobe, in the bottom of the cone is the bottom lobe, and then around that middle, we have around the middle. Okay, really, all I want us to get out of this is that d orbitals generically look like clover leaves, and the dz squared is weird. The only one I want us to know the xyz name for is this. This is dz squared, and the dz squared one is weirder than the other d orbitals. Okay. If we go one more L value, we will get to F orbitals. F orbitals, I call them, the F stands for freaking weird, or whatever other F word you want to put in there. I don't really care about what the F orbital shapes are. Every one of these somehow has 3 nodes in it. I'm not going to draw it. Okay, 3 planar nodes. Some of them are obvious, like here you can see blah, blah, blah. There's 3 planar nodes in there. Some of them are less obvious. Because L equals 3, there's 7 orbitals in the subshell. Okay, I'm not going to test you over what F orbitals look like, so there's no stress there, although you might encounter an extra credit question or 2 about it. Okay, F is weird. All right, this is a great summary slide. This is also where the other picture came from before. Every s orbital is a sphere, right? That means L equals 0, M equals 0. Every p orbital is dumbbell, so that's M equals 1. There's 3 values of M sub L. Excuse me. So there's 3 orbitals there. There's 5 d orbitals and 7 f orbitals. And these are what the shapes kind of generically look like. Okay. As a reference, and this is just to say in a hydrogen atom, so I like these 2 next to each other. We often draw the orbitals as boxes or lines or circles or whatever, just as a way to do the orbital diagrams and stuff, and we'll get into that. But in a hydrogen atom, all of the sublevels have the same energy. So anything that starts with a 2 is all together. Anything that starts with a 3 is all together. Okay, I like this because it also puts the orbital shapes on here as well. So the 2s are all together, right? Notice as the n gets bigger, the orbitals get bigger, right? That's what n does for us. But it also adds a spherical node. So you'll look, there's extra blips in the p orbitals. And if we looked at 4d orbitals, there'd be extra blips in there too. You can Google stuff and look at other complicated orbitals, but I just want us to be able to know what the generic shapes are, right? S for sphere, P for dumbbell, that doesn't actually work. D for cloverleaf, okay. And D has also got the dz squared, which has a donut in the middle, okay. So now we can go beyond Bohr model and we can look at the what we call the quantum mechanical model. I don't know what I just did to my slide. Okay. In the quantum mechanical model, the biggest thing to remember is we tend to forget that if the orbital doesn't have any electrons in it, it's kind of not important to us. We want to remember all of the orbitals exist all the time. Empty or filled, there's orbitals there, okay? And all of the orbitals are centered on the nucleus, so the nucleus is buried down in here, okay? And so if you take what the volume of the orbitals are and overlap them all at the center, you roughly get this spherical shape. And again, most of that is empty space. So we're just defining the volume where the electrons could be, and there's tiny, tiny electrons in here somewhere, okay? It's also important to know that a lot of, and you can kind of see it in this picture, a lot of the lobes of the orbitals, you can't see me pointing, a lot of the lobes in these orbitals are overlapping in the same spot, which is going to lead us to some interesting things later on when we get into where electrons are in the orbitals. Okay. Now, we've talked a lot about stuff throughout this whole quantum mechanics business. Um, just a little kind of quick semi rundown of what I expect out of this, because there's a lot of stuff in here that is interesting and necessary to kind of get us to where we're going, but it's not something I would necessarily test over. We got to know about waves and particles, frequency, wavelength, amplitude, constructive and destructive interference. We got to remember what the double slit experiment looks like and all that fun stuff. We got to know Bohr model, right? The energy level, how the transition between energy levels works, what the energy levels mean. We had to do a calculation like the one we did with, 1 over n squared minus 1 over n squared, that business. You'll be given that equation if we need it. We got to know these people along with Bohr. He could be on this list too. We got to know these people. We just need to know what their big experiment was, what their big idea was. Okay, so Thomson was the cathode ray tube and mass to charge ratio of an electron. Millikan was the oil drop experiment that gave us mass of an electron. No, it gave us charge of an electron, and we can calculate the mass of an electron. Rutherford was the gold foil experiment, which gave us the nucleus. De Broglie was the mass wavelength dude, and the whole number of wavelengths to go in a circle. Heisenberg with his uncertainty principle and Schrodinger's equation and all that. We got to know the quantum numbers. We got to know what the rules are, which is really what I want you to get into. The rules of the quantum numbers, what's possible, what's forbidden, what's allowed, to define what they are, and can you state what the possible quantum numbers are for things? And then lastly, we got to know what the atomic orbitals look like. Can you generically tell me what a node is, and do we know what s,p,d orbitals look like? And can you recognize what an f orbital is? Not necessarily to tell me that it's an f orbital, but to realize it's not an s, p, or d orbital, if that makes any sense whatsoever. All right, that's it for our quantum mechanics stuff, and I'll catch you later.